Hello everyone, today I'm going to give a talk about two negative results regarding the local maximum in the likelihood of Gaussian mixture model. My name is Qijing. This is a joint work with Yuchen Zhang, Shivaraman Balakrishnan, Martin Wainwright, and Michael Jordan. So first, our setting is basically as simple as a Gaussian mixture model, where we assume we have m mixtures. Each mixtures have equal weights, which is 1 over m, and we further assume the covariance matrix all equal to identity matrix. So the only parameter unknown in this setting is the mean of each component, which is mu1 to mu_m. We further assume we have infinite data, infinite samples. And the standard way to estimate this means is by maximum likelihood estimator, which is MLE. And the standard algorithm to achieve this is by expectation maximization EM algorithm. There are two steps in EM algorithm, which E step and M step, which can be found in a standard textbook. In this paper, we also study a variant of standard EM algorithm, which we call gradient EM. Basically, in the M step, we're no longer doing an exact M step, we're doing an approximate step by gradient descent. We further denote the population likelihood by L mu. Because EM algorithm actually working pretty well in practice for Gaussian mixture model, in code 2007, Natty Sabro kind of raised the open problem. He was asking, are there local maximum in the population likelihood? If no, suppose the only thing left would be saddle point and global maximum, and probably it will be much easier to optimize. So our first results kind of negate that conjecture. We're saying as long as the number of mixture m greater or equal to 3, then there's always a bad local maximum. Furthermore, the local maximum can be the log likelihood of those local maximum can be arbitrarily worse than the log likelihood of the global optimum. Our construction is also simple and not very delicate. We're basically saying if the underlying true distribution is something like the black clouds in this graph, and if we're putting 3 standards as the orange dot in this graph, then as long as the distance r is kind of like reasonably large, there are always a local maximum around that configuration. And on the other hand, we also believe our requirement for number of mixture m greater or equal to 3 is kind of like tied, because for 2 mixture and 1 mixture Gaussian mixture model, it's kind of like already known there's no sparse local maximum by a recent paper. So now we know Gaussian mixture model indeed has some local maximum, but people may still wondering, is it possible, like if we're doing some EM or gradient descent, we will like most likely converge to the global maximum? Actually, there are only like small fraction region where you will converge to those bad local maximum. Our second results kind of like also negate that possibilities, and we study a commonly used random initialization scheme, which basically sample all the initial means uniformly from all the data points. And we kind of like saying, our results says random initialization plus EM or gradient EM will always converge, with high probability converge to those bad stationary point. The log likelihood of this bad stationary point can be arbitrarily worse than the global optimal. Furthermore, we are saying these bad stationary points cannot be strict saddle points. That means we're kind of almost certain it's local maximum which is causing the entire problem. So the main takeaway of our paper is twofold. The first one is the Gaussian mixture model is kind of like hard, in the sense we should not hopefully to achieve any global convergence results for local search algorithm in general. Second thing is, in practice, we always recommend to do some smart initialization algorithm like k-means plus or some other strategy. Thank you very much.